Let's start the lecture. This is a joint program between CMSA in Harvard and the Math Center in Tsinghua University, where we invite prominent mathematicians to talk about history and literature in mathematical science. And we have already 4 lectures present in this week, but there are several lectures was done before, 2 in China by Wilbur Smith and John Cox and myself, and also Don Rubin about April. So we are very excited about this lecture. We are thinking to give this kind of lectures annually, inviting quite a few people in different subjects. And today we are very happy to have Robert Griess from Michigan is going to talk about my life and time with the sporadic simple groups. And Bob has been a friend with me for a long time, since 40 years ago in 1979 in Princeton. And around that time, he has developed the major ideas for these sporadic groups, especially the monster group. And the monster group has been tremendously important for mathematics. And I think it would be a monster for a long, long time. The power would be monstrous. And I'm very glad to have Bob starting to give this talk. Bob, oh, we should also congratulate him. He was just elected into the National Academy last week. Okay, Bob.
Okay, thank you, Yao. Yeah, I remember those fun times 40 years ago when we were young and naive and full of idealism, and we've changed a little bit since then.
Right. Get old.
Okay. Well, here's my title, My Life and Times, and I did want it to be a story format in a sense. I'll be writing down some formulas and stating some theorems, but the human side of it is really quite interesting, I think. I was excited. I was there. Okay, let me see if I can use the Zoom command properly. That didn't do anything. Okay. So here's my page 2. All right, so you probably read this abstract. I was the simple group explosion in the 20th century took place in about a 10 or 11 year period, 1965 to 1975, and I started graduate school around 1967, so I was right there and watching all the excitement. It was kind of a pursuit of the ideas, this kind of detective work. It's nice to figure out what was going on, but there was also kind of a scientific experimental side to it. When we had some evidence for simple groups, we wanted to know where to find it. And there were ideas of looking at graphs, looking at lattices, and looking at some other things. So we had to improvise quite a bit. Okay, so let's get started. It's just a little bit of notation. I hope GLNQ is understandable to a lot of people. The general linear group, dimension n over the field of Q elements. These are finite groups. FSG, finite simple groups, and CFSG, classification of finite simple groups. Takes a while to write it out, so I use the abbreviations. And then we've got notations for centralizer and normalizer of a subset of a group. And we get lazy sometimes. We write 2 cross 2 for the direct product of cyclic groups of order 2. To be more correct, I'd write Z2 cross Z2. Okay, let's go on and get started. The term sporadic group was first used, I believe, in the book of Burnside. He wrote 2 editions. This is the 2nd edition. And in the appendix, this book is quite a rich study of the situation in finite groups. And he mentions the 5 Matthew groups. Those are the only sporadic groups known at the time. And he says, these apparently sporadic simple groups would probably repay a closer than they have received. And by the way, Burnside at that time had the opinion that groups of odd order ought to be solvable. And that was something proved around 1959 by Feit and Thompson. So he really had very good sense of the future. Okay, sporadic group is a member, it is a finite simple group, which is non-abelian and does not naturally belong to one of the infinite families like the general, like the PSL, projective special linear groups, or finite orthogonal groups, and so alternating groups, those are part of series. So they sort of stand alone and they need special treatment. And when you first look at them, maybe they could be part of an infinite series, but at this point, we know that that is not the case. Okay. Another term that I want to mention is the word discovery. Amongst the finite group theorists, it meant finding strong evidence for existence. It does not mean proof of existence. That usually came later. The program to classify finite simple groups got started in the early 1950s, and I'll explain that in a moment. And it developed very strongly, especially in the 1960s, and came to some kind of conclusion in the 1980s. The list of finite simple groups has been stable since 1975, and there were some things that had to be fixed in the classification, but that seems to be quite resolved at this point. Okay, now the search for sporadic groups is part of the classification of finite simple groups, but I won't attempt to describe the global developments in the classification. I'll just mention a few things that are relevant. You could think of the classification as mostly trying to prove that if G is a finite simple group, then G is on a restricted list. And some people like myself were interested in creating and proving existence for finite simple groups. So we would contribute to a lower bound, and eventually the lower and upper bounds met. Okay, so roughly that's the philosophy. Okay, most finite simple groups are of Lie type. You can imagine Lie groups, but written over finite fields instead of being written over the reals and the complex numbers. Most finite groups are kind of like that. The symmetric groups, anybody can understand, all permutations on a set of n symbols. But the sporadic groups defy easy descriptions. There are several important themes. I will be describing these, but no one of them covers all cases, and we're missing axioms. We've got themes that kind of describe them, but not axioms like, for example, the axioms of a Lie algebra. Okay, and these themes come in, I put them in two categories. One is external. When we meet groups, they're usually acting on something, like vector spaces or combinatorial objects. The most common themes are these: multiply transitive groups, rank 3 permutation representations. I will define that later. It just means a transitive permutation in which a point stabilizer has 3 orbits. The next theme is isometries of lattices, and I'm thinking mainly of the Leech lattice. It's just one lattice, but it contains a very rich structure. And finally, automorphisms of commutative non-associative algebras. That's where the monster comes in. Now, internal themes. You might think of this as, say, looking at the multiplication table of a group. You're not thinking the group is acting on something. Here's a general fact. If you have 2 elements of order 2 in a group called involutions, their square is the identity, but they're not the identity. If you take any 2 distinct involutions in any group, they generate a dihedral group. So there was a nice theory developed mostly by Baron Fisher that said, suppose you have a group generated by a family of involutions and you restrict the possible structures of these dihedral groups, make them very limited. Well, he got a beautiful theory out of this and discovered several simple groups. And then on the list, actually, for pure group theoretic characterizations, for example, considering a search for groups that have a centralizer of an involution of a certain type. And this is a very large part of the study of the classification of simple groups. Okay, now I'm going to take a look through history, and we'll stop at various years during the 20th century and say what the list of finite simple groups that people knew of looked like. And oh yeah, in some cases, I mention only when these groups were believed to exist. Existence proof may have come some years later. Okay, 1910. Cyclic groups of prime order. Alternating groups. These are the groups of even permutations on n objects. N is at least 5. And then there are some matrix groups over finite fields. And these things were discussed by Galois and Jordan. That's 19th century, but if we just get into the 20th century, groups of type G2 were described by Dixon. I think a lot of people don't know this. He writes down matrices and gets the structure. He also does E6. Now F4 is a natural subgroup of E6. I'm not sure offhand if he did that, but it's possible that he did, at least in fields of odd characteristic. Okay. Oh, sorry, I got things wrong. I forgot about Mathieu. He wrote, I think it was 3 papers from 1861 to 1873, and he described 5 finite simple groups. And these groups are combinatorially amazing. They are, the M24 acts 5-fold transitively on 24 points. If you take the stabilizer in M24 of 1 point, you get M23. And you take the stabilizer of another point, you get a subgroup M22. And there's a similar series, but in smaller degrees. M12, a 5-fold transitive group on 12 points. And M11 is the stabilizer of one of those points. He described them pretty well, but people who studied his papers think that they perhaps wasn't completely clear, wasn't rigorous maybe. And it was treated in a rigorous fashion by Ernst Witt in a well-known article in 1937. Okay, that's what it looked like early 20th century. Now, let's get to 1955. And the reason I picked that year is that Claude Chevalier wrote a very famous paper showing basically how to transfer ideas from Lie groups and Lie algebras to arbitrary coefficient rings. And if that arbitrary coefficient ring is a finite field, then you've got a finite group. His main technique was to use an integral basis called a Chevalier basis. So these things are classified by root systems. So we've got types named A, B, C, D, E, F. Oh, sorry, that should be F sub 4 of Q. And E6, E7, and E8. Okay, Q is a prime power. And A corresponds to the PSLs, and B corresponds to the odd dimensional orthogonal groups, and so forth. Okay. Now, a few years later, Robert Steinberg wrote a paper describing variations on Chevalier groups where you have to consider field automorphisms. So back in characteristic 0, you need complex conjugation to talk about unitary groups. Okay, well, there are field extensions of degree 2 of finite fields, and so you can define a unitary group over a finite field. And the Steinberg groups are listed here. Twisted AN, twisted DN, and triply twisted D4, and twisted E6. Okay. Well, a few years after that, in one of the pure characterization theorems, this is not from the viewpoint of Lie theory, but just pure group theory, Michio Suzuki found an infinite series of were really beautiful things by pure group theory characterizations. Q is an odd power of 2. They might have been considered sporadic, but actually they are groups of Lie type. Takashi Ono wrote a paper proving that. For instance, the Suzuki groups are twisted groups of type B2. And this viewpoint was carried out more successfully by Rimhak Ri, who found twisted groups of type G2, where Q is an odd power of 3, and twisted groups of type F4, where Q is an odd power of 2. The little prime indicates a commutator subgroup. Most of these groups are simple, and there's some funny exceptions sometimes. Twisted F4 of 2 has a simple subgroup of index 2, and it's called the Tits group because he correctly described the structure. Okay, so at the bottom, sporadic count is still 5, just what it was in the 19th century. Well, now let's go to 1970. In the late 70s, there was a tremendous burst of discoveries, and I'll go over these in some detail. The Yanko group, J1, and then a bunch of so-called rank 3 groups, Paul Yanko. The Yanko group J3 is not rank 3, excuse me. And then the other ones are rank 3 permutation groups, Hickman, Sims, McLaughlin, and the big Suzuki group. And then Fisher's theory of 3 transposition groups, which, by the way, are also rank 3 groups. And then Conway's famous study of the Leech Lattice created 3 previously unknown groups. So now we're up to 19. I call this the first half of the deluge. The next part of the deluge is the beginning of the 1970s. And you'll see a lot of stuff happen in year 1973. Now, I was a young researcher at this time, and we kind of liked these interesting groups. And there was a mild depression amongst the group theorists because there hadn't been a new sporadic group found for about 2 or 3 years. The last one was Lyons group. I believe I mentioned Lyons. Yeah, I should have mentioned it. It's at the bottom of that table. And he wrote the paper in 1972, but for a couple of years, nothing much seemed to be happening. And then suddenly in 1973, the group of Onan, the group of Ridvalis, who was found by the rank 3 theory of Donald Hickman, and then Fisher's baby monster in the summer of 1973. And then in the fall of 1973, Fisher and I independently found this group called the Monster. And within the Monster, there are several other previously unknown simple groups. F3, for example, is the centralizer of a certain element of order 3 is a cyclic group of order 3, direct product. This group F3, a new simple group, and a similar thing for the Harada-Norton group. Okay, 25. And in 1975, Yanko, who discovered the first 20th century simple group, found his 4th one, and that's the order. He wrote a letter to Dan Gorenstein, and some of us were gathered at Rutgers for a group theory year, and we got this fantastic news. The final list is this: the cyclic groups of prime order, the alternating groups, all these various groups of Lie type over finite fields, Chevrolet-Steinberg variations, Suzuki and Rie variations, and then 26 sporadic groups. The 5 from the 19th century discovered by Mathieu, and 21 discovered in this intense period, 1965 to 1975. Okay, that was tremendously exciting, believe me. The Monster is the biggest one. The order is about 10 to the 54, and I'll be talking about comparing these groups in various ways. Many groups are quotients of groups of the monster. They could be subgroups, but sometimes the portions of subgroups. The ones that come up that way, the sporadics, are called, form the happy family. And the 6 who are not included, I call the pariahs. And as I said, there's no single theme, but membership in the happy family is a kind of unity. Okay, so that is the answer, quote unquote. And now that we have the list of answers, it's interesting to wonder, how seriously should we take this word sporadic? Well, there's nothing like a sequence of matrix groups. That's certainly an easy description of something like orthogonal groups. The sporadic groups do seem to require special treatment, but there is some fuzzy boundary, and let me mention one. The simple groups of Fisher came from a really simple hypothesis, and that is, imagine finite groups generated by a conjugacy class of elements of order 2. And assume that if you take any 2 of them, they either commute or they generate a small dihedral group of order 6. What are such groups? Well, you've got the symmetric groups. Think of a pair of 2 cycles. If they don't overlap, they commute, and if they overlap in one point, the product is a 3 cycle. That's pretty easy. For finite orthogonal and for finite orthogonal groups, you also have this 3 transposition behavior. That's a little harder exercise. But then at the end of the analysis, you find 3 previously unknown simple groups. This is really amazing. This is to me one of the most amazing things about sporadic groups. That such a simple hypothesis could lead you to those. Oh, and by the way, the subscripts 22, 23, 24 refer to the Matthew groups M22, M23, and M24. So anyway, that's just a side remark. Okay, now let's think about real and complex reflection groups. They've been classified for a long time. You meet the Weil groups when you study Lie algebras. That's a very familiar experience for a lot of people. And when you go to complex reflection groups, the list enlarges slightly. The non-solvable parts of those complex reflection groups are mostly classical matrix groups, so small dimension over small fields. But now how about considering quaternionic reflection groups? Why not? Quaternions are associative division ring, so you can do vector space theory in a sense. And they were classified in the 1970s by R.A. Cohen, and you get the groups you've already picked up as real and complex reflection groups, and several more classical type groups, and you get the sporadic group of Hall-Yanko. Well, I'm cheating a little bit. It's actually a double cover of that sporadic group, and it occurs in, I think it's 3 quaternionic dimensions and 6 complex dimensions. Okay, so here's a fairly classical concept, real and complex reflection groups. You generalize rather mildly and you pick up a sporadic group. Okay, now, there is a classification of omega transposition groups for various sets omega. I'll talk about those later. If you do the so-called 4-odd plus transposition groups, that was handled by Timmisfeld and possibly some other people. You assume the group has no normal solvable subgroups, and mostly what you get are groups of Lie type and characteristic 2, plus one more group, and that is the Hall-Yanko group. And the Hall-Yanko group is actually embedded in the group of Lie type G2 over the field of 4 elements. So that's a surprise. Okay, and finally I mentioned that there is a class of involutions called 2A in the monster, and they satisfy a 3, 4, 5, 6 transposition property, which kind of looks like you know, this kind of behavior for the real and complex reflection groups. Well, not really, I'm exaggerating, but it does have that feeling. Okay. Now, the classification of finite simple groups starts in the early 1950s. So I'll tell you how it got started. I'm just peeking at the time here. Okay. There was a graduate student at the University of Michigan who studied with Richard Brower. Richard Brower was a faculty member at the University of Michigan about 1947 to 1953, approximately that. And he had several students. And the following rather striking theorem was proved. It says, if you have a group of even order, a simple group of even order, then if you take an involution in G, an element of order 2, there's a function so that the order of G is bounded by a function of the order of the centralizer of T. So one way to say this is, suppose H is a given finite group. So you fix H and then look around for simple groups which contain an involution whose centralizer is isomorphic to H. Then the number of such simple groups is bounded. And the answer is usually none, in the vast majority of cases. But so that was really quite striking, and it encouraged people to think about the study of centralizer of involutions as a way to control and understand finite simple groups. The function, by the way, is really too big. It's just it's of no practical value. Brower proposed this viewpoint at his talk at the International Congress in Amsterdam in 1954, and he mentioned an early theorem along this line. So it's a way to characterize the simple groups PSL3 over the finite field of Q elements. Here, Q is an odd prime power. Okay, so the characteristic of the field is odd. Take an involution in PSL3Q. So it's not a matrix, but it's a matrix mod scalars. So take this matrix mod scalars. 1, -1, -1 down the diagonal. And now what is its centralizer? Well, if you just play with the matrices, you see it's all matrices of this form where you've got a 1-by-1 matrix in the upper left. So that's a scalar, little c, and a 2-by-2 block in the lower right. A is invertible. There is no restriction on the determinant of A, but C times the determinant of A is equal to 1. So you play with this a little bit and then go mod scalars, and you realize that that H is isomorphic to GL2Q. If you take that A in the lower left, then it goes on to the image of the centralizer mod scalars. Okay, so that's a good candidate for a centralizer of an involution characterization. So if H is the centralizer of involution in a simple group, what is the simple group? Okay, and so here's the theorem. Suppose G is a finite simple group with an involution U so that the centralizer of U is GL2Q for Q odd. And there's an extra hypothesis. Sometimes this happens early in the game. This hypothesis was removed later. Assume for any element in the center of the centralizer that is not the identity that the centralizer in G is the same as the centralizer of U. Then G is what you expect, PSL3Q, or Q is 3 and G is the Matthew group M11. This is the smallest sporadic group that is order 7920 and order 2 to the 4th times 3 squared times 5 times 11 is the factorization. And the punchline here is if you'd never met a sporadic group before, you would meet it this way. Okay. Now, this sort of characterization was done for many, many other cases. And there were some times when there was a surprise. There was a kind of a generic argument, and there was a funny branch where you couldn't do something with one of the equations, and it led to an exception, a previously unknown finite simple group. Okay. Okay, so here's another example of an early characterization. This comes from the early 1960s. Take Q to be of any prime power greater than or equal to 5. And G is a finite simple group with abelian CLO 2 subgroups. So that's an extra hypothesis. And an involution with prescribed centralizer, the direct product of a group of order 2 with PSL2Q. Conclusion, Q is an odd power of 3, and it's at least 27, or Q is equal to 5. Now, the case Q equals 5 was eliminated when Yanko and Thompson first considered this. And it was eliminated because there was a character table which gave a contradiction, and the character table was erroneous. The character table was for PSL211. And because of this, the case Q equals 5 was passed over. And Yanko and Thompson separated ways, and then Yanko came back with a treatment of that case. When Q is equal to 5, assume CG of T is isomorphic to Z2 cross PSL25. Then G is a simple group of order 175560, which has that nice factorization. 2 cubed times 3 times 5 times 7 times 11 times 19. And his paper had the discussion of conjugacy classes in the character table. Such a group was constructed by John Cannon on a computer as 7x7 matrices, and maybe not at first, but he eventually proved that it was inside the Chevrolet group G2 over the field of 11 elements. It's one of the Chevrolet groups over the field of 11 elements. So, a characterization by centralizer of involution leads to another unknown simple group. Now, this was in 1965, and it caused quite a shock, and it was before my time. I mean, of course, I was still alive then. I was alive then, but not studying group theory quite so seriously. It meant, what did this mean exactly? Was it a hint of more sporadics, or would it be part of an infinite series, the way the Suzuki series was? Well, the order of GLNQ is a polynomial, and similar formulas for other finite groups of classical matrix groups. So maybe this J1, which has this nice order, and it has a factorization like this, is part of a series of groups of order Q times Q plus 1 times Q cubed minus 1, where Q is a power of 11. Beautiful idea. It didn't work. So now I got this from an article of Jacques Titz. If you take this number, you can factorize it as a product of 4 consecutive numbers and a product of 3 consecutive numbers. Looks like fun. I don't think anyone has done anything special with that. Okay. I see I'm getting some questions. Maybe I'll try to deal with the questions during a break. Now, J1 has a subgroup isomorphic to PSL211, and it has index 266. That's 2 times 133. 133 is the dimension of the E7 Lie algebra. Could this be connected to E7? Well, J1 is in G2 of 11, and G2 is contained in this series of the algebras. So there's some kind of a with E7, but nothing very close, nothing more than being inside G2 of 11. Okay, so there was some imagination going on, but nothing seemed to work of the kind I listed. Okay, now, the strategy of using centralizer of involution characterizations or looking for new finite simple groups, you can't just try all possible finite simple groups. You have to be clever and restrict things in a good way to make some progress. And but still, it's kind of amazing looking back on this that some of these groups, they're not that big really, and they yielded some very interesting new groups. Take this group. It's got a normal subgroup of order 2 to the 5th. It's a so-called extra special group and extended upwards by a group of outer automorphisms, the alternating group of degree 5. Okay, Yanko took this one and he looked at it and saw that it had 3 conjugacy classes of involutions. There's an involution Z in the center. And in this normal 2 subgroup called O2C, there is another class of involutions. And then there's a 3rd class of involutions outside O2. So it's in the upper part of the group, you might say. The Glauberman Z-star theorem says that Z must be conjugate to at least one of these others. Now, if Z is conjugate to just one of them, then Z is conjugate to W in particular, and the simple group that results is the Hall-Yanko group. And the case where Z is conjugate to both W and T leads to another group, J3. It's really amazing. So he got 2 simple groups with the same centralizer of an involution. Now we come to a really striking example. Dieter Held looked at a group that was the centralizer of an involution in the matrix group, GL52. You can think of it as the 5 by 5 matrix that is the identity, but then the upper right-hand entry, change that from a 0 to a 1. And you get an element of order 2, and the centralizer has this form. And it was known to be a centralizer of an involution in the Matthew group M24. So he did a characterization expecting the conclusion to give those 2 groups, but he actually found a 3rd group as well, the so-called sporadic group of Held. So amazing, really quite amazing. So the number, I see I made a mess on this formatting here. The number of finite simple groups have a particular group as an involution center is bounded. That number can get as large as 3, and that's in the case of these 3 groups, and otherwise the number is less than or equal to 2. So we know that only after the classification of finite simple groups. Now, Yanko went through many candidates for centralizer of an involution, and he was a professor at Ohio State for a while. He had a weekly seminar where he came in and brought in his current cases, and he gave them a pretty good workout in the seminar situation. During that period, he did not find a new simple group. And he even considered series of centralizers. If you look in the middle of the paragraph, there's this group 2 to the 1 plus 8 SP62. That is an actual involution centralizer in a simple group, the second Conway group. Well, why don't you rub out the Q and replace the 2 and replace it by a Q. Q is a power of 2. So you've got a whole series of groups, maybe one for each Q. There could be a sporadic group. Nope, that didn't work either. At a 1972 meeting in Gainesville, Florida, I remember seeing him there, he proposed another infinite family of centralizers, which seemed to survive at the moment. But weeks after that, and the meeting was done, they were eliminated. And in his conference proceedings, he does not describe that infinite family of centralizers, but he describes yet another family of centralizers. And the theorem is that the possibilities are very limited. He was quite an energetic person in working the centralizer of an involution theme, I must say. Now, the Donald Hickman rank 3 theory. Okay, so we have a basic situation here. G acting on a set omega. G is a group. So there is a homomorphism from G to the symmetric group on the set omega. And we're going to be doing finite situations here. So the set omega has finite cardinality, and it's called the degree of the representation. The rank of a transitive permutation of the group G on a set omega is the number of orbits for the natural action on pairs of elements, omega cross omega. And because of transitivity, it's the same as the number of orbits of a point stabilizer on omega. G sub A is the set of group elements which take A to itself. That's a subgroup. So you don't expect it to have as many orbits on G as on omega as G does, of course. It's got a single point orbit, but on the remaining points, we're assuming it has, I'm sorry, the number of orbits on the remaining points is called, I keep saying it wrong. It's the number of orbits on the point stabilizer. The doubly transitive case is that there are just 2 orbits. So rank 3 is just the case beyond double transitivity. Okay. Now I am going to introduce some notations. There'll be some numerical conditions that we have to consider. Okay, so Gx and omega. There are 3 orbits for a point stabilizer on omega. One is just the 1 point set A, and then the other 2 are called big delta of A and big gamma of A. And I assume that when we transform by an element of little g, the delta sets are stable. Okay. So I define these numbers, n, the cardinality of omega, k, the cardinality of delta, l, the cardinality of gamma. So n is k plus l plus 1. And then there are these 2 funny numbers, lambda, the cardinality of the intersection, delta of A and delta of B, when B is in delta of A. Now, if B is a point different from A, it doesn't have to be in delta of A. It could be in gamma of A. Well, then you get another number, mu, for this intersection. And these numbers do not depend on choice of B in delta of A or in gamma of A, respectively. Okay, K degrees and the quadruple of points are called the Hickman parameters. Now, if there is a rank 3 group and you define these numbers, then some accounting argument gives you the following condition, the Hickman condition. So this will be coming up a couple of times. Now, you can just take a set of non-negative integers and see whether or not they satisfy the Hickman criterion. It might be true. Those numbers could come from a rank 3 group, but not necessarily. And Don Hickman kept a long list of such quadruples. His article, or his theory, I should say, has a lot of other numerical conditions, but I don't need to talk about those. Now, here's one that's easy to visualize. I'll be mentioning more difficult examples in a minute, but just take the symmetric group of degree m. M is at least 4. And actually, G just has to be a 4 transitive subgroup. So it acts highly transitively on omega, so it's rank 2 on omega. But you can look at it acting on unordered pairs of distinct integers. And that gives you a new set The cardinality of the new set is m choose 2, m times m minus 1 over 2. And the action of G on that is rank 3. If you take the stabilizer of a point, let's say ij is a pair, it acts on the set of pairs that are disjoint from ij, and it acts transitively on the set of pairs that contain exactly one point, ij. And you do all this counting, and you plug it in, and you can just check that the Hickman condition is verified. Okay. Okay, now we're getting into some sporadic stuff here. So we'll have a break in about 10 minutes maybe. Okay, 1967, the Hall-Yanko group was in the works. Yanko and Marshall Hall independently discovered this group. Yanko did it by a centralizer of an involution characterization, which I described a few minutes ago, and Marshall Hall thought of a rank 3 permutation group in which the stabilizer of one point is this nice little group, PSU33, a group of orders 6048. And he found a graph on 100 points with valency 36. And the group H operates on it with 3 orbits. And he showed that there was a larger group that acts transitively on it, and the stabilizer is this group H. So now some computing work was done in this. David Wales and Marshall Hall constructed one of these with a computer. And they knew about each other's work, and each of them wrote a paper acknowledging the work of the other person, so which I thought was a very nice thing to do. Okay, now shortly after that came the Hickman-Sims group, and the story takes place over just about 2 days, I would say. There was a conference in Oxford in 1967. Marshall Hall gave a lecture on his construction of his simple group, HJ, and it acted on a rank 3 fashion on a graph with 100 points, valency 36. So on the last day of the conference, the 2nd of September, Hickman and Sims thought about this number 100. We use the decimal system, so 100 is culturally very meaningful to us, and wondered if that number could come up in other ways for rank 3 groups. Well, there's an easy example using symmetric groups. You can kind of do this in your head almost. You take the direct product of 2 symmetric groups of degree 10, acting on the Cartesian product of 2 sets of cardinality 10. They each act as a symmetric group on those components, and then you can take an involution that flips the components. So the group you get is the wreath product, and it has 17 and 81. So you can calculate that during the break and check the Hickman criterion. Whoa. I jumped too far. Okay, here we go. Now, Hickman had a table of Hickman quadruples, and one of them was this sequence, 227706. The 0 is that number lambda. K and L are the first 2. Those have to be positive, but lambda in principle could be 0. So this happens. Now, the number 22 suggested the Matthew group, and the reason it didn't suggest the symmetric and alternating groups is that they don't act on a set of 77 points. So you had to have something special. Okay, so they wondered what this would be, and the combinatorialists know about the Steiner system, S of 3, 6, 22. It's got a collection of blocks of size 6, so that any choice of 3 points is contained in a unique block. So how many blocks do you get? Well, you can pick any set of 3 points out of the 22, but once you achieve a block, you can get it by any 3 points within that block of 6 points. So 22 choose 3, dividing out by the repetition, 6 choose 3 gives 77. Okay. Well, they defined a graph. You connect a point to delta of that point. So the delta they picked to be the 22 points where M22 acts. And M22 acts on the associated 77 blocks. So there's your big gamma. And the automorphism group of M22 actually acts on this set of 100 points. And they referred back to the work of Ernst Witt, who cleaned up the theory of the Matthew groups and made it rigorous and accessible. Now, how do you make a graph on 100 points? Well, star is connected to the 22 points of delta. Take a point in delta, you connect that to star, of course, but also to the 21 blocks containing it. And what do you connect a block to? You connect it to the 6 points in the block and the 16 blocks that are disjoint from it. You have to sit down and do all this counting to see that those numbers are right. And that gives the Hickman parameters, lambda equals 0, mu equals 6. They needed to prove existence of a permutation which preserves the graph and moves star to one of the other points. That'll give you a transitive group and a rank 3 action. They stayed up all night. It's fantastic. They got the idea during the day. They stayed up all night. And by Sunday morning, the 3rd of September, they had a new group. They weren't sure if it was simple or whether a subgroup of index 2 of it was simple, but it was clearly different from all the known simple groups. Fantastic. The time from conception to existence was about 1 day. That record has never been beaten. It's fantastic. Don Hickman passed away in year 2006, and so some of us put together a memorial issue for Don, and we did various research, and it turns out there is a statistics doctoral thesis at Michigan State by Dale Messner. Some of you may know the name Bose Messner for some combinatorics, from 1956. And he was dealing with association schemes and Latin squares. And he basically cooked up the Hickman-Sims graph. And from his viewpoint, he had actually 4 ways to construct it. He did not know whether or not they were equivalent. He did not attempt to determine the automorphism group of this system, but he did get the graph. And so that was a big surprise that came out. Just found out 10 years ago. Given the Hickman parameters, when is there a rank 3 group? Well, this viewpoint was paying off. I have a book on called 12 Sporadic Groups, and Don gave me a table of his that has lots and lots of these parameters, so you can look it over. But was there at graduate school, and Jack McLaughlin was visiting from University of Michigan. He had a sabbatical, and he was certainly aware of the Hickman-Sims group. Don Hickman and Jack McLaughlin were colleagues at my university and good friends. So Jack McLaughlin thought about the group H, PSU43, which comes up in the theory of complex reflection groups, by the way. Anyway, it's order 2 to the 7, 3 to the 6, 5 times 7. It's a group of Lie types, so there are parabolic subgroups that are accessible. There's one of index 112. And so he said, well, how about it? Can 112 be one of the Hickman parameters? Now, if that's true, L must be the index of a subgroup in H. And he thought about the ones that he knew, and he remembered an old paper of H. Mitchell of a subgroup of index 162, and that subgroup is isomorphic to PSL34. And if you plug those into the Hickman conditions, there'll be a few unknown parameters. It's very easy to determine the remaining ones. Lambda equals 30, mu equals 56. McLaughlin defined a graph on 256 nodes, valency 112 at each node. And in the same spirit as Hickman and Sims, he defined an automorphism of the graph that moved the single point and was therefore in possession of a new sporadic group of order 2 to the 7, 3 to the 6, 5 cubed times 7 times 11. Yanko came around that time to the University of Chicago. He was on his way somewhere. He stopped to give a seminar. And I was at the colloquium dinner party, and Jack and Doris McLaughlin were there laughing with Yanko, and they were both pretty happy about their simple groups. And I think George Glauberman was there. I don't have a clear memory about that. Yeah. And as I said, a lot of the classification attempts, careful study of the arguments led to branches that involved some new discoveries. Yanko was probably the champion of this for the type of characterization by centralizer of an involution. He tried so many of them. He was successful 4 times, which is as much as anybody, I think, including Baron Fisher. And his success was with centralizers that people just wouldn't have thought of offhand. And the biggest one is down on the page here for the pariah J4, a group 2 to the 1 plus 12 times 3 times M22 times 2. Now, how did he think of that? I have no idea. But that was just amazing. And of course, he gets better and better at it each time he has a success. Okay, I wonder, this might be not a bad place to pause and have a break of 5 minutes or so. So let's see, it's 14:01. So let's say, oh, I don't know. At 2:10, does that seem reasonable? Hope you can read this. Okay, now I think I have to do some stuff with the commands here. I'm going to mute for a few minutes. Okay, goodbye everybody. I'll see you in about 5 or 10 minutes. Can everybody hear me? I'm going to answer some questions. I can't tell, I'm not getting an answer.
We can hear you.
Good, all right, I'll answer these questions. It's 10 after. A question, are there Octonian reflection groups? I don't know, that's a good question, but since they're not associative, it's difficult to do linear algebra type module theory with them. So that's my short answer. If one interprets a result that M11 in some sense belongs to the family of groups PSL3Q, can one consider several of the other sporadic groups to belong to some family in some way? Well, I suppose you could consider the first Yanko group, but it has a centralized sort of a cyclic group of order 2, direct product PSL2Q. And there's an infinite series of those things when Q is an odd power of 3. That's the groups of retype for the family G2 in characteristic 3. So there are a few examples like that. Last question, which group was the one arising from K equals 1, 1, 2? And the answer is McLaughlin. McLaughlin was doing that process, and I neglected to say that the group he achieved was named the McLaughlin group. So I think I've answered all the questions. If you're still not happy, send me an email and I will answer it later today. Okay, I think I want to go back to the Sharing screen. Okay. Oops.
Looks like you're sharing your desktop there, not the the slides.
How about that?
There we go.
Let me just test to see if I can advance and go back. It seems to be okay.
Looks good.
All right, everybody. Well, welcome back. I hope your break was exciting. Okay. One of the themes that I mentioned, the external theme at the beginning, one of the that covers many sporadic groups, is the Leech Lattice. And boy, this is a really important object. It's important in number theory and combinatorics and group theory. I'll give you the group theory history. It was discovered by John Leech. I remember meeting John Leech at one time. And he defined it. It was pretty obvious that it was a very dense sphere packing, but he didn't know how to analyze the isometry group. And I think he asked a few people before he finally came to someone who was willing, and that was John Conway. And the rest is history. Okay, so let me give some definitions for okay, I'm moving this little window here. You can't see what I'm doing, but okay. A lattice is a z-linear span of a basis in Euclidean space. Integral means all the inner products are integers. It does not mean the coordinates of those n-tuples are integers. And it's even if all the inner products are integers and the self-inner product is an even integer. Okay, now given a basis for a lattice, a Gram matrix is the n by n matrix whose determinant is vi dot vj. And the determinant of the lattice is the determinant of any Gram matrix. Okay, now some number theory tells you a lattice is even in unimodular only if n is divisible by 8. And there are classifications of all of them explicitly, dimensions 8, 24, 8, 16, and then 24. And in 24, there are 24 of them. They all have roots, vectors of self-inner product equal to 2, except for one of them. That's the Leech lattice. The minimum norm there is 4. Okay, and capital lambda is a common notation for this. I have to keep moving this thing around. Okay, Conway tells the story that once he got the challenge, he sat down and he figured it all out in one session of 12.5 hours. I've heard accounts from other people that say there was a little uncertainty about the group order, maybe at least 2 candidates, but it was resolved quickly. And the order of the isometry group is this fantastic number. And as linear groups go, the isometry group is pretty big. There's no, in any dimension, there's no size to the, sorry, there's no limit to the size of a finite linear group. But if you assume that there are no non-trivial normal subgroups outside the center, then it's limited. Okay, the isometry group is sometimes denoted Conway sub 0. Okay, now, here's a standard description of the Leech lattice. You start with a square sublattice. So it's got a basis. The basis consists of norm 4 vectors, each vector dotted with itself as 4. And any 2 of them are orthogonal to each other. Okay, so it's a so-called square lattice. Then take an orthogonal basis VI, and capital omega is an index set. And now take a GoLay code. This is a linear subspace of binary vectors of length 24. It's 12-dimensional, and the minimum weight of a non-zero vector is 8. At least 8 ones appear in a vector if it is not 0. Okay, it's a non-trivial fact that this thing is. So you start with your square sublattice and you make your, I think it was, what did I call it, J? And then I see I made a typographical error. Let's call the original sublattice M. So now further down the page, I define N by taking the Z-span of M and all sums that look like 1/2 V sub capital A. A is a subset of omega corresponding to a word in the GoLay code. If you take a binary word, if you just take the index set, we get all ones. That's a subset of the index set. Okay. So you take the sum of those VIs that where I is in A, and you do that just for capital A's in the GoLay code. You take the Z-span of all those things, and you get a slightly larger lattice. And then to get all the way to the Leech lattice, you take what I just said, and then you take the Z-span of the single vector minus VI plus 1/4 V sub omega. Okay. There are many definitions. For a lot of computational purposes, this is very, very commonly used. Okay. Conway gave an explicit formula for an isometry, not in this monomial group. I think I may have jumped. Yes, sorry. The group M24, famous Matthew group of 24 symbols, acts on the index set, preserves the basis, and you can choose an M24 that preserves the GoLay code. So you preserve, I see I changed names again. It was M and N, now it's J and K. Okay. Please forgive me. Okay, and then it turns out M24 preserves capital lambda. And then there's a group of sign changes where you change the signs at the VIs if and only if I is in a certain set S of the index set. And it turns out it preserves the lattice if and only if capital S is a set in the GoLay code. Okay, so this is a nice little exercise. So you put all these together and you get a monomial group, a semi-direct product group of order 2 to the 12 times M24. And then Conway gave the formula for an isometry that is not in that monomial group. And you have to check some things, but it's not very difficult. And coincidentally, you can prove that the isometry group has to be bigger than that monomial group by use of the mass formula, but that doesn't help computation, especially. I wrote my own treatment of the Leech lattice that really minimizes the calculations of matrices and counting arguments. And it's kind of a game where you have one sublattice and you want to look how many ways can you blow it up to a slightly larger lattice with certain properties. And by playing this game very intensely, I got a theory of the Leech lattice. The paper is called Pieces of 8. Now, consequences for finite group theory. The quotient of Conway 0 by the scalars plus or minus 1 is a simple group of this big order. And if you stabilize certain sublattices, you get some new sporadic groups, Conway 2, Conway 3, and you rediscover some old ones. Well, they're not that old, maybe a year old. Hickman, Sims, McLaughlin. And Hall-Yanko is not the stabilizer of a sublattice, but rather it occurs as a component and centralizer of a certain element of finite order 5. And for Suzuki, you get a double cover of Suzuki as a component and the centralizer of an element of order 3. Okay, it's kind of technical to write that stuff down, so I'll just leave it at that. Okay, so terrific. So on this page, we've got 7 groups. And you add that to the Matthew groups that are already in there. So you've got 12 sporadic groups in the context of the Leech lattice. Fantastic. Okay, now we come to the last of the major themes that I mentioned, the group theory. So Fisher really got this going. But let's start with a very general concept. Take a non-empty subset of the integers greater than or equal to 3. It could be infinite, that's fine. In any group, 2 involutions generate a dihedral group, and you can characterize the dihedral group order by just taking the product of those 2 involutions and looking at the order of that product. If you've got your set of involutions greater than or equal to 3, called omega, an omega transposition group is a finite group generated by a union of conjugacy classes of involutions, so that if you take any 2 of them, then they either commute or the product has order, a number that's in the set omega. Okay, so this can get pretty wild. So you would imagine if omega is kind of nice, you can get a reasonable theory. And that's roughly what happened. Take the case omega is just 3. This occurs for the symmetric group, transpositions in the symmetric group. And actually there's an extra case when n is equal to 6, but let's skip that. And then you get some cases for orthogonal reflections over the field of 2 elements, and then for some classical groups over fields of 3 elements. And Fisher didn't classify all such groups, but rather the ones that had some nice conditions, like every solvable normal subgroup was the identity, or maybe in the center, I've forgotten exactly. When you push this theory as far as you can, you find that there are 3 additional sporadic groups. And by the way, Fisher 24 is not simple. It has, the commutator subgroup has index 2, and it's simple. And I'm quite impressed by this fact. Yeah, and these groups, these 3 Fisher groups are 3 transposition groups. So in a sense, they could have been swept out by inspired searchers with Don Hickman's 3 transposition, rank 3 theory, possibly. Okay. Now, if you take omega to be 3 and 4, if you take GL and 2, the conjugacy class of transvections, which have Jordan canonical form displayed as in a 3×3 matrix, then any 2 of them generate a dihedral group of order at most 8. And then some sporadic groups also meet this condition. Conway 2, Baby Monster, possibly some others. Now, it turns out if you say, oh, I can do something with any choice of omega. Well, it seems to be pretty hard. Take the Suzuki group over the field of 8 elements. It's really not that big. It's about a 5 or 6 digit number. It has 1 class of involutions. 2 involutions commute, or their product has order 5, 7, or 13. And the product of trying to classify such things is, okay, you know what's going on if you pick 2, but what if you pick 3? You want to sort of see what happens and things overlap. And it's just too hard when you cannot count on hitting a rather small number. 5 is getting to be too big. Okay. Yeah, concerning computer constructions, I don't really have a great deal to say in great detail, but let's take the early 70s when Charles Sims tried to construct the group of lions in Onan. He was dealing with computer work in sets of cardinality, what, 8, 9, or 10 million, something like that. I forgot to write this down. And the permutation rank was not rank 3, but maybe 4, 5, 6. There just wasn't a lot of theoretical rigor that could be imposed on the situation. So it was pretty much computational power that was a big factor here. The Root-Vallis group was a group. It was discovered by search. Root-Vallis was very fortunate. It has a subgroup of small index. Conway and Wales did construct it by computer work in a couple of weeks. Pretty good achievement. But 4060 is really not very big compared to the permutation degrees necessary to deal with some of these other groups. Okay. And in some cases, computer constructions were removed by people who did finite geometries. Okay, now we come to the group that I worked on quite a bit. Bernd Fischer and I discovered it fairly well independently of each other. We knew each other. We had good conversations in the past. I got a letter from Ulrich Dempfwolf, who I think was at a Oberwolfach meeting. Anyway, Fischer had evidence for a new group, and there were some sketchy details circulated. It had this order. And so I thought about it, and you have to understand at this time, there was just a flood of information about these new groups with no obvious theory that organized them. So it was a challenge, and it also made me tired as soon as I read his letter, but I thought, okay, it might be interesting to work on. Well, I didn't right away, but I did get around to it months later. And my thoughts were, okay, Fischer shared some properties of this putative group, not known to exist at that time. There was a centralizer of an involution. Near the middle of the page, you'll see 2 to the 1 plus 22, Conway sub 2. Okay, to me, that suggested blowing up to a larger group, 2 to the 1 plus 24, extended upwards by Conway 1. Well, okay, why not? H contains a subgroup 3 to the 1 plus 10, PSU 52. And I thought, well, let's blow that up to the Suzuki group. So all this stuff started coming together pretty well. And I want to make a comment about putting ideas together. There are a lot of advantages when you're dealing with a group that's small, because you can, so to speak, list everything and write it out. Well, not really, but you have an idea that you can kind of grasp the whole. That's not true in a really huge, complicated thing. However, the structure that's carried along to put it together comes with its own nature. It has a life of its own, and thinking that Conway sub 2 fits inside Conway sub 1 set off some other suggestions in my mind. So it's not terribly surprising that someone would think of this. So I worked on this, and I couldn't get a contradiction. And I think it was around the first weekend of November in Ann Arbor when I thought all my speculations were coming together, and it was a pretty good chance that there would be a new sporadic group. And I didn't know this, but there was a meeting in Bielefeld the same weekend, and Fischer spoke about his ideas. We didn't talk to each other about this for weeks or months. I don't have a clear memory when we next met, but he was also actively thinking about his 3-4 transposition theory, and he was more into it than I was, so that was one of his advantages. Okay, now, Monstrous Moonshine. This changed things a lot. Let me describe it, and then I'll make some comments about context. John Mackay noticed that the number 196884 was 1 plus 196883. And I'll say, that's easy to check, and you'll all laugh. Okay, 196883 to the group theorists was familiar. That was the candidate for the lowest possible matrix representation for the monster in characteristic 0. And a side comment, in characteristics not 0, it could be smaller, and it is. 19688 2 for characteristics 2 and 3. Steve Smith and I worked it out once. But you can't find a small way to describe the monster by matrices. So Mackay said, hey, there's this elliptic modular function that seems to have something to do with sporadic group. And Thompson got interested in this, and he looked at these higher coefficients and said, oh, these are simple, non-negative integer linear combinations of irreducible representations of the monster. And it went on for some time, and he didn't prove a theorem. He just said, this seems to be true. He conjectured that if you make a graded space like this, where of modules for the monster, then the traces of non-identity elements, I'm sorry, the dimensions would give you the elliptic modular function with the adjusted constant term. Thompson felt that the series, when you take traces of non-identity elements, could be interesting. And indeed, that was extremely interesting. This story was put together by Conway and Norton, and you probably know that both of them passed away recently. And it really created a lot of excitement, and it also created a feeling that sporadic groups may be more connected with the rest of mathematics than was obviously the case. You know, we were getting a lot of, you might call, very technical group theory information without any anything to ground it in other parts of mathematics. You've got all these numbers and these situations because the theorems say that that's so, and that's all you get. Okay. Now let me talk about the possibility of a construction. The fact that the moonshine business came around made me reconsider the idea of a construction. It's not obvious, it wasn't obvious how to do that, because if you take two matrices of size 196883 by 196883, it takes a lot of computer time to multiply them. And you don't just multiply two matrices and watch and you get a theorem. You have to be able to manipulate a lot of situations. That would have been taxing the limits of computers around the 1970s. And the same thing for large permutations. Because the monster was becoming more important, and because there was a feeling in the late 70s that the classification of simple groups might come to an end, there was an articulation of a final set of procedures. It was relatively explicit. So people were thinking, well, maybe it's the end. And the last sporadic group that we'd seen was 1975. And a few years after that, I thought, well, maybe the monster really is the biggest one. But it was important for cultural reasons. It's connected to all this number theory. So I thought it may be a good time to consider constructing it. When it first came around, a lot of people thought you could waste a lot of time on this and have no reward, and there may be even more larger and larger sporadic groups and maybe no end. I mean, why knock yourself out for something that might give you a very small payoff? One group theorist told me that he or she could have articulated the beginnings exactly as I had, no problem. This person felt they were obvious, but this person didn't want to do it because they thought it was just a thankless job and probably wouldn't amount to much. So, and this is kind of what I just said. The picture changed. So I decided to try, and it was about 6 years or so after the discovery and the there wasn't anyone who really felt they were going to jump in and try to do anything seriously. A lot of people would have liked to do it, but you need a good idea. And I thought the best idea was to use this partial representation, because Simon Norton had done some work on it. If B is such an irreducible representation, if B exists, he computed some traces of elements, and he did enough so that in his feeling, B was self-dual and it had a degree 3 invariant symmetric tensor. So B would therefore have the structure of a commutative algebra with an associative bilinear form, and the monster would act as algebra automorphisms. This is important because this would mean matrices giving the monster wouldn't just be lucky choices of matrices, but they would have to satisfy a condition. They would preserve the algebra structure. So, and that was an extra edge, and then it was very critical. Okay, so now a definition. We in finite simple group business identify groups by like to identify them by their centralizer. So we say a group has monster type if it has an involution whose centralizer has the expected form 2 to the 1 plus 24, extended upwards by Conway 1. And by the way, there's more than one such group. I'll say something about that later. One of them works and the other one doesn't. Okay, so I take a suitable group C of this shape, and because it's put together in a nice way, and then we know something about the Conway groups, we know some things about its representation theory. So I consider a reasonable representation of C on B, and then I make a choice of algebra structure amongst all the C invariant algebra structures. You can classify those. I have to pick a good one that could be invariant under a larger group. Then I define an invertible linear transformation on sigma, which preserves the algebra structure and is not in C. And then I show the group generated by C and sigma is a simple group of monster type. So that would clearly indicate that I had found a new simple group. Now, a few words about C. You could think of it as a fiber product. So in the lower right-hand corner, let me just check the time, I'm okay. In the lower right-hand corner of this square, this diagram is the simple Conway group, and to its left is the isometry group of the Leech lattice. So that arrow is just the quotient map, mod the scalars, plus or minus 1. Now for the arrow coming down, think of this extra special group, 2 to the 1 plus 24. We know about extra special groups that has a unique irreducible representation. It's of plus type. I didn't write that, so it's even rational. So in general linear group of degree 2 to the 12, comma, rationals, you can see a copy of this extra special group, this little finite group that acts irreducibly. Well, its normalizer is very rich. The normalizer includes the scalars, but if you forget the scalars, the normalizer induces on it the full automorphism group of the extra special group. So you can descend inside that automorphism group and find a copy of this simple group of Conway. Think of it as acting on the Leech lattice mod 2. That's a representation of degree 24 over the field of 2 elements, and it leaves invariant a quadratic form. Okay, so that's all I will say about that. So that's called C infinity. Now, what's C? We'll take the direct product of C0 and C infinity, and then take all pairs in that direct product such that the 2 components map to the same thing down in the lower right. So it's kind of twisting the multiplication in C infinity a little bit. Okay. So here's my B, the 196883 dimensional space. It's a sum of 3 pieces, U, V, and W, with these dimensions, 299, 98280, and 98304. And the conway of the Leech lattice acts on 24-dimensional space by orthogonal transformations. It leaves invariant quadratic form. So it acts on the symmetric tensors and leaves invariant the symmetric tensors of trace 0. Maybe I should say symmetric matrices. Okay, so 25 choose 2 is 300, subtract 1 dimension for trace 0, you get 299. The V in the middle is kind of interesting. There are 196,560 shortest vectors in the Leech lattice. And if you pair them up, lambda comma minus lambda, you get the number 98280 of pairs. So imagine a vector space with those pairs as a basis. And W is the hard one. We have to act faithfully on W by C and think of this construction here. The C infinity has a representation of dimension 2 to the 12, and the C sub 0 has a representation of dimension 24, and if you tensor them, you can get a representation for C. So I'm waving my hands a bit, but that's roughly the idea. Okay. Now, if X and Y are these 3 things, oh, each of these 3 is irreducible. Maybe I didn't say that for this group C. So I want to study invariant forms and algebras, invariant under C. So I have to look at Hom sub C of X comma Y. And I'm sorry, I wrote this incorrectly. It should be X tensor X prime comma Y. That's what I should have written, where X, X prime, and Y are in the set UVW. Okay. That will help you give a multi-parameter space of all C invariant algebra structures. Now, you have to have some insight to pick a good one that's likely to have a larger automorphism group. Well, there's a lot of calculation involved, but what group theory says, if the monster exists, there would be a subgroup K of this form, 2 to the 2 plus 11 plus 22 to 22, and the quotient is M24, direct product symmetric 3. You don't see that inside C. The best you can do is get a pretty big intersection that's 1/3 as big. In the right-hand factor, symmetric 3, drop down to the symmetric group of degree 2, you might say. That you can see inside the group capital C. And so my sigma interacts with a big piece of the group C, but not all of it in a direct way. So that was my viewpoint. Oh, sorry, I may have skipped ahead too quickly. Sigma is not expected to leave U, V, and W invariant, but if you take some direct sum decompositions of U, V, and W the right way, you can imagine sigma permuting these pieces around, like it might switch a UI and a VJ, or a VI and a VJ, or a UI and a W, or something like that. Well, maybe a VK and a WL. You can imagine a series of things like that, and that gives you an idea, rough idea of how sigma works. And actually, that was good enough to pin down the algebra structure. So I need an exact formula for a linear transformation. I've named the algebra. So I pick a basis, a reasonable basis, and I compute sigma of the product of the 2 B's times, and compare it with the product of sigma of the first B times the sigma of the second B. I see I left off a parenthesis on the left. So that's a lot of writing, and it took me about a week to do one trial run. And it was a disaster at the beginning, but I learned a lot of things. I used a lot of bandages to patch things up, and it just got better and better. And there were some errors after success because it was really a headache keeping track of all this stuff. And for safety, I would sometimes change a basis and run the same set of calculations with a different set. Instead of the little b's, I would use a different basis, little b primes. So I had a fair amount of confidence in what the answer ought to be. Okay, and I was really working like crazy. I was living on candy bars and working around the clock, watching junk television. I did go to the Institute, which was very nice at lunchtime, and people were very friendly, and that was a nice time. Bombieri noticed that I was doing, and he took a lot of interest in me, and was very friendly and very supportive. So I did appreciate his caring about this. I wanted to beat the New Year's, but I couldn't do it. So it went over 14 days, and then I was ready. I had a short announcement typed up. One of the staff members did that, and I mailed it to a lot of people, and then I got a lot of phone calls and mail back. So that's the story of how it happened. Oh yeah, I did have to write it up for publication. That's more misery, but I won't talk about that too much. It was unique. The monster is unique. That was proved only later by myself, Meyer Frankenfeld, and Segev. We thought Simon Norton had proved it, but he didn't get around to publishing it, and then he agreed that there were some gaps. So, okay, this is what happens, big classification, and you have to check everything and maybe go back and redo something. Okay, now I'm pretty good on time. Now we're going to talk a bit about moonshine. This graded space that Thompson envisioned was actually created by Igor Frankl, Jim Lepowski, Arnie Marmon in 1983. They used very sophisticated highest weight theory for affine Lie algebras, and they blended that with the paper I wrote on the construction of the monster and got something. The Lie algebras were kind of there in an intermediate role. Maybe this is not quite right, but it helped guide how the monster ought to act on the entire space. The piece of that space that I dealt with was just the first non-zero term of dimension 196884. I didn't see the rest of it, but they did. Okay. So they did this, and when Borchards promoted the theory of vertex operator algebras, they said, oh no, we have to redo this and make it not just a graded space, but a vertex operator algebra. Okay, that was more work, but they did it, and they put out a very nice book, which is a standard reference. So careful work. Now, I'm not going to attempt to describe VOAs. I'll just describe a few things. It's a graded space. I'll just take the simple case, graded by terms greater than or equal to 0, with a countable sequence of products, one for each integer, positive and negative. The kth product gives a bilinear map that on V, and if you use products VI and V times Vj under the kth product, you land in V sub I plus j minus k minus 1. Go figure. Okay, that's the way it works out. So the space V sub n under the n minus first product is closed under that product. So it's a finite dimensional algebra. And the algebra that I defined would be there V sub 2 under the first product. This V is a general V, but I mean the one that they built recaptures the algebra I defined. Okay, and by the way, there is some nice general theory about VOA. Finitely generated VOA is an algebraic group, something worked out with Chong Dong. We studied a lot of properties of VOAs, just mention a few of them. And nope, sorry. Okay, I'm close to the end. Graded representations for other groups. Well, a lot of people have tried, but there was a recent candidate that looks pretty interesting. They got one connected to the Onan sporadic group. It's a pariah. And sorry to say, Mike Onan has also left us right around the time we announced it, unfortunately. And it has number theoretic properties. We don't know that it's closed under any products. Well, at least I personally don't know. And the kinds of number theoretic properties are for the series, the weight 3/2 modular forms. I call this Onan shine. I don't know if those authors will like that term or not. And you also get some moonshine for the group J1 because J1 is contained in the Onan group. It's the fixed points of an outer automorphism. Okay. There are integral forms in VOAs. I've been involved in a theory of integral forms and have papers with Chong Dong and Qinghong Lam. There's, in the case of the monster acting on the moonshine VOA, there is an integral form which is invariant under the monster, but even better, one which is self-dual by work of Carnahan. If you have a lattice type VOA, if L is a root lattice type ABE, the integral basis that comes from the theory that Dong and I established, if you take that integral form and intersect it with a degree 1 term, you recapture the Chevrolet basis, the standard Chevrolet basis. So it's an absolutely natural generalization. Next question, is every finite group the automorphism group of a VOA? It sounds like Nota's question for Galois groups. And the answer is we don't know. It's true for the monster and just a handful of other groups. There was one funny one that came up that wouldn't have been. This group, E6 of 2, is a Chevrolet group. It's not involved in the monster. But the semi-direct product, a group of order 2 to the 27 with E6 of 2 comes up. This is work of Shimakura, I believe. Well, if you care, I've got references. So just let me know by email. And for positive characteristic, you can use the standard integral form in those lattice type VOAs to do Chevrolet theory, get Chevrolet or Steinberg groups over finite fields over finite fields. So for fields of positive characteristic, you have a positive answer for this Noether type question. The group is a Chevrolet group extended upwards by diagonal and graph automorphisms, not field automorphisms there. And I'm happy to say there's a short existence proof of the monster and the moonshine VOA. There is a theory of Miyamoto about simple current algebras. And basically what it means is that if you look at the space of intertwining operators of that with other irreducibles, the dimension of that space is, I think, 0 or 1-dimensional. I hope I've got the correct definition. So if you take a VOA that has a module like this, you can take the direct sum and make a slightly larger VOA. That's a little surprising, but it comes from the simple current theory of Miyamoto. And Shimakura showed that you can build the moonshine VOA this way. It's really relatively painless if you believe in this kind of representation theory. And Qinghong Lam and myself used that to give a relatively short existence proof of the monster. And all those long, nasty calculations in my papers and other people's papers can be ignored. So that's really quite pleasant. So this is the direction that I've been looking in, VOA type theory, and people are making use of sporadic groups in many different ways. It's really quite an interesting time post-classification. But anyway, I wanted to give a report on my own experience. I have 2 minutes and 30 seconds left.
Okay.
It was a pleasure to talk to you and respond. I think I have to do something to see the.
Yeah, well, thank you very much, Bob. So let's have some questions and answers. I guess you can see the questions.
Yeah, what do I keep forgetting what I have to do here. You are screen sharing.
So you can end your screen share now that you've come to a close, and make it easier to find the Q&A box.
Stop share? Okay.
Yeah.
Okay, good.
So now you want to find the taskbar and find Q&A.
I see, I have Q&A, and I've answered some of these Q&As before, so let me. I seem to be, I'm sort of scrolling round and round. Let me just start with this one. I have a question from Alonia Carolina Ivanova Arroyo from Colombia, and says, I'm curious about the Brouwer-Fowler theorem. I don't understand why the involution is limiting the group. It's a proof in elementary group theory. It's elementary, believe it or not. And I can refer you to a publication. I can't do it here just talking, but send me an email and I will get you a reference. Noam Elkes says, where does Conway's M13 fit into this? I don't have a thoughtful response to that. I'm sorry. And what else do we have? Zhangzhu Lin, the group RU seems to come up differently. I'm sorry, different from what? I guess I don't know what that means. Oh, can you hear me?
Yeah.
Zhangzhu Lin? Okay. How do the group RU comes up differently? I don't know what that means. Noah Melkis, did you hear my previous answer? I may not have pressed the right button. No answer, okay. I think I've done all the Q&A, and there's a chat section as well.
Right.
Let me click on chat. Oh, sorry, I do find a new Q&A. Are you in car? Is there a connection between the nature of the work and rather romantic naming conventions? No, not really. Short answer. Okay, all right, let me put this aside and go to chat, see what happens there. Robert Bryant. Now, do I type an answer for this? Is that it?
You can just answer it verbally. That's okay.
Can I verbally? Okay. Robert Bryant says, were there any G2 of Q groups separate from this list? I don't know. I'm sorry, I don't understand the question. G2 of Q. I'm sorry, Robert, if you would maybe ask the question in a slightly different way. Sorry, I don't get your meaning. Okay, and Noah Melkis says, typo, thank you. How can I find a list of participants? I don't know. If you would email some of the organizers, they'll direct it to the administrative people. Then the question, if quaternionic reflections give the Hall-Yanko group, is there a way to push the step further and define an octonian reflective group, reflection group that gives something interesting? And the answer is, I don't know. But the first problem to dwell on is that the octonians are not associative. So the vectors things that we're used to doing will be rather troublesome by comparison. I don't know the answer to that. I wouldn't be surprised if someone attempted it, but I don't personally have an opinion. Okay, Noah Melkes doesn't trially twisted D4 or 2 or something like it show up as a reflection group of the octonian plane? I don't know. There is a classification. Now, the octonian plane. I don't know offhand what the answer is, but there is a classification of finite simple groups that are embedded in the exceptional Lie groups. And there are tables, and you can look up and find this group, trially twisted D4 of 2. I wouldn't be surprised if it's in if it's one of those groups, and that may help answer your question. Can I comment? Next question, CT McCullen. Can you comment on Matthew Moonshine related to automorphisms of K3 surfaces? And the answer is no, I don't have any special involvement in that. I don't have any special opinion. I think I'm done with the chats. I see some numbers popping up in Q&A. Let me click on that and see what happens. Close chat, click on Q&A. I still have another question about Ridvalis, and I'm sorry I still don't know how to answer the question.
Well, maybe you can communicate with him by email later.
Yes, anyone who cares to talk further, you're very welcome. Send me an email, rlg@umich.edu, and I will be happy to talk. And,
okay, this is the most inspiring talk in group theory for me. I have known you for more than 40 years. When you discovered the moonside, I was in the Institute for Advanced Study too. We have a large group of geometers working on various things in the Institute when you discovered the monster group. And I was very pleased that you play volleyball with us also, Bob. That's very nice of you. Thank you very much.
it's a pleasure.
So let me announce that the next 2 talks will appear in May 22. Bong Leung actually will talk about the moonside related to vertex algebra. And we have a talk by Manoliska from Stanford on 4-dimensional topology. That will be May 22nd, a Friday. So thank you very much, Bob. Really enjoy it. Thank you. Bye.
Bye, everybody. Thank you.